let's get started. First, by going over the answer key a little bit. So the first problem is based on different ways of measuring GDP growth, and there was a short paper talking about it. The differences, essentially you can measure economic growth by the amount of stuff purchased or by the amount of income received. And those two concepts should be equal to each other in theory, but they're never equal to each other in practice the way the government estimates. And that's, I think, a little bit jarring to a lot of people, or a lot of maybe media people perhaps, where, if you saw like the news today, you'll see it reported, GDP for the fourth quarter of 2022 was 2.7%. As if like a whole bunch of people in the government counted up all the transactions. But the U.S. economy is like $25 trillion a year. And even in a quarter, nobody is counting up everything. So it has to be estimated from and modeled. And so, one of the arguments made by people who want like everything to be migrated to the blockchain is like, if hypothetically everything was, then you could calculate like world GDP exactly, because all the transactions would be recorded both from the side of the sender of the digital tokens and the side of the recipient of the digital tokens. And it would just like all be added up automatically. Every like digital coin comes with its whole transaction history that can be verified, using blockchains and whatnot. But it's not at all clear that that's worthwhile to be keeping track of every transaction that perfectly, because like costs a lot of energy and all that just to do. It takes a long time to verify any Bitcoin transaction at least. And so, and then you wouldn't be able to really divide it up by country, because like all the countries would be on the blockchain. So anyway, that's like a hypothetical thing that does not at all match the reality of what the United States does when it estimates these things each quarter. Now, it's all the more disheartening that the media and whatever would say like GDP growth was 2.7% in the fourth quarter of last year because the government says so. When the government in question, in this case the United States government, goes out of its way to say this is not a particularly reliable process. This number is going to get revised 5 times, before it eventually becomes like set in stone. It often contradicts an equally valid measure for gross domestic income that also gets revised 5 times. And moreover, like this data is an estimate from a model of GDP, rather than some pure accounting thing, because you're never going to be able to count up all the transactions in a $25 trillion economy that's integrated with the whole world economies and all that. And so, statistically speaking, this is definitely an estimate. But the 2.7 business that you would see doesn't come with any uncertainty. Doesn't come with like a posterior distribution. To quantify, well, how likely is it that it was, this much higher, this much lower, stuff like that. Now, the people in the US government who produce these estimates, one, they're transparent about what the model is, like you weren't required to dig into the details of what the model is for this homework, but those details are available for people with a lot of training in macroeconomics that they can look at. Moreover, these are done by career people in the Bureau of Economic Analysis, not political appointees, and so the stuff that you might see on the internet about like the United States, like, fudging the numbers to make Biden look good or something. None of that is, true. But, it is, like they say, a not perfectly accurate process. Moreover, this idea of, well, GDP growth is like officially what the government says it is. Outside of OECD countries, which have some standards and some like harmonization of how they do these things, and there's probably like 25 or something, 30 OECD countries. Outside of those countries, that's a terrible idea to just take the government's word for something like this. In part because in a lot of cases, those countries lack the capacity to come up with like reasonable inputs to a model for their GDP. They just don't monitor anything well enough to really have a good sense of what it is. Compounded by the problem, a lot of the governments have no inclination to be transparent or honest about what they're estimating anyway. And like even maybe in some cases, like the central government might have some incentive to try to get this right. They can very well be lied to by subnational governments like states or cities or something like that, whose incentives are not the same as the central government. So it's not as if these numbers that are put out by governments are completely worthless. They're just not the truth. They're estimates, and they could be systematically distorted estimates. But they can be conditioned on in a model that allows for the possibility that the true rate of economic growth is not exactly equal to those things. Essentially, measurement error models. And, with this problem, and especially the second one, emphasizes idea that would have been completely crazy to Fisher and people like that, that the data are not objective. Now, Fisher was a biostat person, primarily interested in the results empirically in agriculture experiments. And so you can see why, if your thing is like, okay, if I put this sort of fertilizer on an apple tree, how many apples will it produce? You get a basket, and you go and pick the apples, and you count the number of apples in it, and then you compare it to another tree who didn't get the special fertilizer in its apples, and you count the difference, and you get an estimate, and you could see how someone like Fisher would think of himself as collecting objective data. Like you just look in your basket of apples and count them. Like there's no disagreement about what that would be. But if you try to count a $25 trillion economy, or you try to count the number of carbon dioxide molecules in the atmosphere, that's not the same thing as counting the number of apples in a basket. And so you're not going to be able to do that, like literally counting on your fingers. this sort of stuff. And so what gets considered to be data on GDP or greenhouse gas emissions or a bunch of other stuff is not objectively counted data. It is subjectively guessed, measured, estimated, something by people. And when you look at it that way, then Fisher getting all bent out of shape about the lack of objectivity of Bayesian analysis due to the prior seems overwrought, as basically everything Fisher said seems overwrought if the data aren't objective either. But Fisher was pushing this distinction that like science has to be objective and deductive. But there's certainly a lot of areas where like that's not even possible, even if you didn't have priors, because you have data that are equally as subjective and human created as priors might be. Now, Fisher did most of his influential stuff in the 1920s and the 1930s when social science as we know it today did not exist. And so even if he were like inclined to think about, lack of objectivity in psychology data or something like that, there was no psychology, social science for him to be like, oh, well, that's not exactly the same as what I'm doing. So it wasn't even on his radar screen. Social science in its modern form basically got started in the late 1940s, even though like retroactively we sort of consider some things before that to be like precursors of social science. But by then, Fisher was like mostly retired and lobbying for the tobacco industry and stuff like that. But anyway, so what's further kind of, okay, so maybe we'll give Fisher a little bit of a pass on that because like social science and GDP accounting, like none of that existed when he was writing these, harshly critical of Bayesian ideas, things in the 1920s and whatever. But we shouldn't give a pass to all the social scientists in the 1940s and 50s and later who just uncritically tried to adopt what Fisher said and apply it to the social science without really, considering the fact that social science data in particular tends to be a lot less objective than what Fisher and Neyman, people like that, thought data to be, the way they conceived of data when they were saying, this stuff about the subjective versus objective take on probability. And that is, one sense in which the Bayesian approach to quantitative methods is perhaps more applicable in the social sciences than it is in some other subfields of science, although it continues to be applicable in pretty every field of science, but especially the social sciences. Because what we consider to be data is just another form of belief about what the data were, or what like the true data values were, that we can update as we get more like contaminated data values. And we alluded to that a little bit with like, how much missing data there is, how much measurement error there is the first week. But as we get a little bit more social science bent in this class, start to see these issues coming up a little bit more. So anyway, first part of the first question, choosing a prior for tau. That could be anything in the ratio of 4 to 9 for A to B, but bigger numbers imply more prior certainty about that. So you could sort of think about it that way. Also need a prior for the Okun's law part of it. So based on the change in the unemployment rate, so in the fourth quarter the unemployment rate went from very low to even lower. by negative 0.19, and so that would correspond to slightly above 3.2% for the expected growth in that quarter if Oken's law were to hold. And okay, so Oken's law is not actual law. It's an empirical regularity that was observed to hold reasonably well during a long-ish stretch of time by a guy named Oken. It's just like other people call it Oken's law, but it was not at all deductive. It's not like Boyle's law or something like that for chemistry. Empirical relationship. But it's, it holds decently well. That was like R squared of 0.45 or something like that on Wikipedia. So you need to choose a value of V that sort of is consistent with how well Oken's law holds. And that's not something that's super obvious how to do. But if you turn to the next question, drawing from the prior predictive distribution, so this is what your model believes reported data will be for GDP and GDI. And then you can sort of fiddle around with the A and the B and the V until you get something like, oh, well, that's plausible for what the reported data could look like. But the reported data could differ from what you expected to be for two reasons. One, like the truth could deviate a little bit from what Oken's law says has been estimated in the past. And like the GDP, GDI report by the government could deviate from the truth. So there should be like a decent amount of uncertainty here. This is maybe, if anything, too much. Like nobody really thinks GDP growth was greater than 7% in the United States, or nobody really thinks it was negative in the fourth quarter of last year, although some people were predicting it to be before it happened. So this is maybe a little bit too uncertain, but something like this I think would be reasonable, and it's going to be centered at the Oken's law relationship, a little bit above 3 in light of the fact that unemployment rate declined. Now, I meant there for to be GDP and GDI, but I forgot that in the fourth quarter it takes them even longer to come up with the estimate of GDI, so we just condition on GDP here. And this business of, well, okay, the data reports it to like 1 decimal place, but the draws of GDP that we got from the prior predictive distribution have 16 decimal places. So if we just said like, when is it exactly equal? Never. But if we allow for the fact that this is only reported to 1 decimal place, so there's plus or minus 500ths between like what the government's model said and what the government like reported in its press release, then I mean this is fine. It's not how we would do it like for real. In part because if we had like a few data points even, then like none of the draws would satisfy even rounded relationships if there are like a few observations. But I mean this is fine for conditioning on what was reported this morning, and then get a bivariate plot. This one didn't come out as well with the colors as I would have hoped. But you have this bivariate set of beliefs about mu and tau. Yes?
So I have a question. Why every time I was going to rerun this particular function for 1.4, you give me like a different graph? Like
yes. So the draws change because they're random. If you call the set seed function in the first chunk, then the draws won't change. I think the plot is deterministic given the draws.
Yeah.
But anyway, even if yours was coming out like a little bit changing every time, the general idea, you ought to be able to get from this, where again, it's, centered maybe around 3-ish mostly. But now there's like essentially no chance of it being negative or greater than 6 after having conditioned on a moderately reliable data point. Okay. So I said last time, or before we read Lancaster, that for historical reasons, Lancaster parameterizes the normal distribution with the precision of the normal rather than the standard deviation of the variance. And the reason why that is true is because it is a bit easier to obtain a closed form solution in a situation like this if you parameterize the normal with the mean and the precision. And this is an example where you didn't have to do this, but the priors actually are conjugate with the likelihood, and this is one of the very few examples where we can come up with a closed form solution when there's more than one unknown parameter. And I gave a link to the derivation, but the short version of it, A in the prior becomes A star, B in the prior becomes B star, so that A just gets updated by A over 2. B star actually gets updated by the data. V in the prior becomes V star is V plus n, and M in the prior becomes M star, which is V times the prior M plus N times the average of the values in the data divided by V plus N, which was V star. And the predicted distribution is in the student T family. Not going to get into the details about that. So in this case, we actually only ended up with one data point on GDP. But we can confirm the facts that I asserted. If we calculated the average of view in the posterior draws and then compare it to the M star, it is the same up to like simulation error. And then, if we do the same thing for tau, the average of the draws for tau are equal to, well, it's not really V star, that's a misnomer, but A star divided by V star, which would be the posterior expectation of tau, and again, it comes out the same. So this is a case that could have been done by analytical solutions. But the paper that motivated this advocates the use of gross domestic output, which is the average of GDP and GDI growth. And if we'd had GDI growth, then we could have actually computed that. But GDO, if n is 2, so you have a GDP and a GDI, let's say, then X bar would be the average of those, which is just GDO. And then if you look at the formula for like M star, let's say, so we have V times the prior M plus N times GDO divided by V plus N. And so what the paper advocates, just relying on, or mostly emphasizing GDO as the estimate of economic growth to combine the GDP and the GDI, which are like theoretically just as good as each other, but they differ. Well, that is a special case of this if you set the prior V equal to 0. So then you have 0 plus n times x divided by 0 plus n, and it's canceled, and you're just left with x bar for GDI. And so it would be relatively easy to, plug in your A and your B and your V and to get a posterior distribution over true economic growth. If V were 0, that means you're putting 0 precision and since precision is the reciprocal of the variance, infinite error variance on Oken's law. Even though Oken, I think he's dead, but he's basically been made into a saint among economists, and no economists actually believe that Oken's law has no predictive power at all, which would be what you're saying if you put a precision of 0 on that. But there's approximately 0 economists who use Bayesian ideas in their empirical analyses, even when, like in this case, there actually is a closed form solution that, economists certainly can be able to handle the math of. But they just don't want to. Even though that would get you like a whole posterior distribution of beliefs about this unknown thing, capturing your uncertainty about it. But instead what economists do, when they get something that's kind of at odds with what their prior beliefs like would have been, they're just like, I don't really think that's right. Probably future revisions of this data is going to bring it like closer to what I thought. So it's not as if they lack beliefs. They just lack the wherewithal to put their beliefs into the framework that was designed for belief management in the basic. Questions about that first one? Okay. Second one, climate change. So this generated, I think, a little bit more confusion than I hoped. So one is this idea that the authors of this paper, Stevens et al., a whole bunch of authors, came up with their prior on equilibrium climate sensitivity by having this random fraction with a normal prior about the numerator and a normal prior about the denominator. And so that implied some distribution about the ratio of those things. And the ratio of those things is the ECS, equilibrium climate sensitivity, in this model. So you can do that. And then they said, oh, well, actually what we meant is just like the region between 0 to 10 of this, and that was like, 94% or something of it. So that was like not a super big deal, but they probably should have said that in the paper before it got published, and then they had to make a correction to it or whatever. So over the 0 to 10 interval looks like this. Okay, it's a little bit skewed. And like that's mathematically fine. Scientifically speaking, it's putting a not small amount of probability on the ECS being greater than 5 degrees Celsius or Kelvin, same units. And if it's going to be more than 5 degrees, like that's a problem. That's a big problem. So having a prior distribution with this much uncertainty about it is not a comfortable situation to be in. Like we would really like to know what this ECS is with more precision. But that's not the easiest thing to do. Or well, conceptually it is, you just use Bayes' rule. But how you use Bayes' rule is not the easiest thing to do. Particularly because we're talking about, the atmosphere and like the top of the atmosphere. Where, we don't have as good a handle on everything that's going on up there. Then So the next question was to derive the PDF of a ratio if the numerator and the denominator are different normal distributions that are independent of each other. You can just kind of plug in the formulas on formula on Wikipedia, and in order to check that it's correct, even though the problem didn't require you to check that it's correct, it just required you to do something that's correct. You can integrate this from negative infinity to infinity, and the PDF, if you've typed it in correctly, must integrate to 1. Now, side note, the mathematical form of the PDF conveys virtually no intuition about the random variable. It's just some function that's not negative, and it integrates to 1. So the units of it are sort of whatever units makes the thing integrate to 1. Moreover, a PDF doesn't have any particular relevance at any one point. Even the mode, which is like the value of the PDF that's the highest, is not very relevant. It's actually more of a red herring. But the PDF is used as a weighting function over the whole parameter space. So it's used like inside definite integrals and stuff like that. So insofar as it's relevant, it's sort of relevant for putting the whole sample space into the function, not just like one point. And they're really best plotted rather than obsessing about the numerical form of these things. But anyway. So then as we get to going with the posterior distribution, the authors sort of assert, which is fine, likelihood function that's equivalent to what you see here, involving evidence E and like a theory C, and depending on the true equilibrium climate sensitivity chi. So this is a function of chi to be evaluated at the observed values of E and C. And they go in the text of the paper, explaining how they came up with these E values, which are basically probability of the true ECS being like as low as low as 1.5 or higher than 4.5. In light of the theory and the evidence and stuff like that. And in a bunch of places, they're like, well, it's unlikely that the true ECS is greater than like 4.5 degrees because nobody's been able to come up with a computer model that has that amount of sensitivity in it when like you put all the other stuff in the computer. And that's, I guess, true. I don't even know, but I presume it's true. Well, yeah, but it is still, even maybe more so than the economic growth thing. This is the author's subjective assessments of theories. That's what their data is that they're conditioning on. And in fact, the prior on the ECS, this ratio business, is a lot more objective than the data were. Like this was the fraction and like the numerator and the denominator business was based on like some physics experiments that people had done in the lab or whatever. And, maybe these numbers are like not totally right or whatever, but the idea of defining the ECS this way has some like theory and it had some like, physics experiments and stuff behind it. So of the two, the prior was much closer to something that scientists would say is objective than what the authors of this paper used as their data, which was basically them saying, oh, well, this theory is that theory is like more or less unlikely because it predicts like this and this and this, and those things aren't really happening. or they're not happening in computer models, things like that. But anyway, these are data and we can use them to make a likelihood function, which can then be multiplied by the prior to get the numerator of Bayes' rule. So in this case, we have 6 data points that are considered or assumed to be conditionally independent of each other, given the true but unknown ECS chi. So to define a function for the numerator of Bayes' rule, we just take the prior density, which is this ratio of normals business that you got from Wikipedia, and multiply it by the likelihood function of chi, evaluated at the first data point, whatever this scenario was that they said was probably only a 25% chance of that being true in light of, you know, their arguments and whatever. And then do it for the second thing, the third thing, the fourth thing, fifth thing, sixth thing. So this whole thing together, multiplied together, is likelihood over the whole data set. And then we have prior based on, you know, experiments and whatnot for the ECS. Then to obtain the denominator of Bayes' rule, we just integrate that over the entire parameter space, which in this case they restrict to the 0 to 10 interval to exclude some of that stuff that I guess no one really believes. And then divide the numerator by the denominator to get the posterior density that can then be plotted alongside the prior density in figure 2b of the paper. So to do the prior and make it integrate to 1, because it doesn't integrate to 1 naturally from the 0 to 10 interval, we have to divide by what it does integrate to, which was the number of draws that we kept divided by r, so that was like 0.94 or something like that. But then the blue, the posterior PDF, that just gets its denominator by doing the integral. And we get a more concentrated posterior distribution about the ECS than the prior distribution that they started with. Yeah.
Why don't we also have to correct for the truncation in the joint probability function?
Right. So that happened, like we do, but that happened because we just integrated the numerator from 0 to 10 instead of negative infinity to positive infinity.
I guess I was wondering why, like in the numerator function, why isn't it e ratio chi over like 0.93 or whatever it was?
Oh, you could do that,
Okay.
but then it would cancel when you do that integral of that same thing in the denominator.
Okay.
So that's why we see in Lancaster, it seems a little bit weird and like wrong the first time you see it. It's just like, ignore the constants. Because any constant in the numerator is going to be a constant in the denominator, and thereby it's going to cancel theoretically. And so when you do like this, post, because it's constructed this way, would integrate to 1 over the 0 to 10. But anyway, so you should get something that looks like this, which is what they had in their figure 2. And so we get, doing this, we get more certainty about what the ECS is. Still too much. And so this paper, okay, the Stevens paper was more intended to be like a teaching thing. Yeah, this is how you could combine all these sources of information with like the theory, which in their case is the priors, in order to come up with something that's, you know, more concentrated. But that was like overly simplistic paper for actual research about the atmosphere and stuff, intended to be so. But there's some other people who picked up on this general approach of Stevens, and they wrote a paper in 2020 that used a lot more than 6 data points and incorporated a lot more theory, estimated a model, Bayesian techniques, but with multiple parameters, unknown parameters, besides just the ECS. Now that paper, it's in like the Journal of Geological Physics or something like that. And so, we couldn't do a QMSS homework about that. It's just like the climate atmosphere business is too complicated. But this paper was influential in the most recent intergovernmental panel on climate change, often abbreviated IPCC, that comes out every few years, and it has estimates of like how much the global warming is going to be. And it's intended to spur governments to stick to or even like strengthen their commitments to phasing out combustion engine cars and planes and stuff like that. So this paper was pretty influential to that group. And they put a 2/3 posterior probability on the ECS being between 2.6 and 3.9 degrees Celsius. 1/6 chance being lower, 1/6 chance being higher than that. And so, I don't even know enough about atmospheric stuff to say if that was like right or wrong. But I do know that if you were to like come up with an example of a situation in science that is intended to, as much as possible, make frequentist approach look ridiculous, it would be climate change. So, like, in a manner of speaking, which is a ridiculous manner of speaking, like the frequentist Fisher approach to climate change, he wasn't worried at all about climate change in the 1920s, but if he were alive today and saying the same stuff, it'd be like, oh, well, you get a bunch of planets that are, have oxygen and stuff to sustain life. And then, you randomly select some of those planets and double the amount of carbon dioxide in them over like 100 years. And then you wait 100 more years and then measure the average temperature of those. And then compare the planets where you doubled the amount of carbon dioxide, how much temperature they increased, and then compare it to the control group for all the planets where you just didn't mess with the atmosphere. And then you get an estimate of the ECS that's objective. And it's also a randomized experiment, which sounds even better. Problem with that, we don't have a bunch of spare planets with atmospheres that have oxygen and reasonable temperatures lying around to do Fisher's experiment on. Moreover, we don't have 200 years to wait to see the result of this experiment if, in reality, the temperature increase here on Earth is going to be more than 5 degrees. So, in other words, you pretty much have an N of 1. And nothing was randomized. So nowadays you can get data on like temperature or whatnot, going back a long way from like trees or fossils or stuff like that. But do we really think some dinosaur was randomizing which fossils got collected or anything like that? No. So N = 1, no randomization at all. And we need to decide in the present what we're going to do in order to shape the future, because there might not be that much future left, realistically. And it gets into another problem, even with this, it's not a problem with the Sherwood, it's a problem with people in the media and whatever, So you say something like, okay, there's a 2/3 chance the temperature is going to increase by 2.6 to 3.9 degrees. But there's a 1/6 chance that it's going to be lower than that. I think a common reaction among people who might not be so inclined to do that much about climate change anyway is to say, well, there's a 1 in 6 chance it's going to be less than like 2.5 degrees increase. You know, we probably could manage that, you know, reasonably well if it was lower. So let's just, you know, wait and see until we get some better estimates of this, you know, before we do something like crazy, like mandate all cars have to be electric or something like that. That would be like disruptive and costly and politically sensitive and all these other things when, you know, maybe we'll be okay if we just don't do a whole lot. Or not us, but like the next generation. They might be okay. Or conversely, you know, it's been observed that if people, you know, climate activists and whatnot, you know, emphasizing, well, there's a 1.6 chance it's going to be greater than, or 1 out of 6 chance it's greater than 4 degrees. And if it were, then yeah, we're pretty much cooked. Big parts of the Earth would be uninhabitable. And trying to get like billions of people all living in Canada, because like that's the only place that has, you know, reasonable temperatures, probably would not turn out well. And so on one hand, there's like a decent chance like we're going to be okay. And there's like a decent chance that it's sort of too scary to even contemplate. And both of those don't really tend to spur people to act. But one of the things that we've been learning in this class is that Bayesian approach applies or links up perfectly with decision theory. So how do we make a decision about what to do in the present in light of our posterior distribution about how much the temperature is going to increase in the future? Well, we need a cost function. How costly would it be as a function of the ACS temperature increase? And then we take a posterior distribution and we apply our cost function to that, and then we apply the expectation to the cost function. And then we see, okay, this is what the expected cost would be if we like do nothing. Here's what the expected cost would be if we, you know, did a lot of stuff in terms of electrification and tighter regulations on factories and like farming and all kinds of things like that, that are also going to have costs associated with it, like economic costs. But basically, if you apply a cost function to any sort of a posterior distribution like this, that's putting a decent chance on the temperature increase being 3 degrees or higher, and you apply the cost function over the whole thing, which would include the region to the right of 3 degrees, the costs of that just become astronomical. Like we would literally have to get into quadrillions of dollars of costs. And so the expectation of the cost of climate change over a posterior distribution like this is huge. And it makes the idea of, oh, let's spend like $1 trillion a year, every year, between like now and then, to try to avoid something that has a decent chance of being 3 degrees, 4 degrees, is a bargain in the decision theory frame. So yeah, the costs are uncertain, but the expected cost over this somewhat uncertain posterior distribution is known to be huge. huge relative to $1 trillion a year to try to avoid that. And so that's the like Bayesian case for like making serious action on climate change. But it was the same for serious action on COVID or whatever else with like the lockdowns and the mandates and all that. The expected cost of COVID, if it like totally spun out of control in the United States or whatever, would have been like trillions of dollars. So the idea of, let's spend billions to try to, or let's cost billions with lockdowns and all sorts of things to try to like flatten the curve and all this and that, seemed like a bargain, or should have seemed like a bargain from a decision theory perspective, based on the expected cost of these highly skewed things that get even more highly skewed if you apply a cost function to a skewed thing, like how many people are going to get infected, or how many people are going to have to like move from where they live to Canada to like avoid droughts and stuff. But anyway, so just wrapping up on the Fisher thing. This Stevens paper, Sherwood paper, and all what, those are exactly the things that Fisher feared science becoming. Entirely subjective assessments by individual researchers, or just saying like, here's my prior, here's what I think the data are like, and then using Bayes' rule in order to come up with subjective posterior distributions about like ECS, with nothing at all being objective, nothing at all being randomized. But scientists do this. There's no mention of any, like, there was one sentence in the Stevens et al. Paper, like, we use the Bayesian approach. No big discussion as to why or anything like that. It's just sort of routine. It made sense for them to do. But it's exactly what Fisher wanted to prevent from taking hold in science in the 1920s and the 1930s. But, particularly with the climate change thing, among a million other things, but especially with the climate change thing, what else are you going to do? How are you going to do science of climate change objective? With an N of 1 and no randomization. And like, yeah, you have to get it right in the present in order for there to be a future. Questions?
So you said that Fisher is like obsessed with making science objective, right? But wasn't science at the beginning subjective, as imagined by the Greeks, when they just wanted to explain like nature and laws of physics through axioms at first and hypothesis?
Yeah, I think science probably never was as objective as Fisher wanted it to believe or believed it was. But you could understand a little bit if your like extent of science is agricultural experiments, nothing involving people, nothing involving people doubling the amount of carbon dioxide in the atmosphere, then you could see how you could fool yourself into thinking that maybe this was more objective than it was. But for the problems that scientists, and like a lot of this is not social science, but there's definitely a social science component to climate change with the politics and economics and psychology and all that. It definitely seems like a more useful framework it's important to be able to quantify your uncertainty, which a lot of this like artificial intelligence, like supervised learning stuff, tries to avoid doing. So that's not really going to work either. All right. Okay. So if we then pick up for today, I'm going to start talking about Hamiltonian Monte Carlo after I put this up. So we're actually going to be starting to talk about Stan a little bit today. So this is perhaps more applicable than it was in the previous weeks. So let's review a little bit quickly the previous weeks. One, Bayesian approach is a belief management system. It thus is completely general. It applies to economic growth and it applies to climate and everything else. But Fisher said science should be about truth. You know, everything's true or false. And we should be proceeding deductively. Only making probabilistic statements about things that we personally randomize. And science shouldn't be about anyone's beliefs about how much the climate or how much the temperature is going to increase like 50 years from now. Or anyone's beliefs about what economic growth was. Or anyone's beliefs about whether your full house is going to get beat if you call Nolan raised or anything like that. Bayesians use probability just throughout rigorously. Indeed, Bayesians maintain that the objective way to update your beliefs is to use Bayes' rule. But the Bayesian approach does not specify how your initial prior beliefs come to be. And that's kind of an important point. I mean, obviously that's what Fisher objected to the most. But irrespective of like whether you use Bayes' rule to arrive at your beliefs now is a good time to start using Bayes' rule to update those beliefs as you get more information in the future. So in Bayes' rule, the beliefs come from outside. There's no restriction on how you came to believe what you believe currently. It's just, okay, this is what you believe currently, not saying anything about whether that makes sense. Here's how you should update your beliefs going forward as new data arrives. And so about the only thing that Bayesians require about the prior beliefs is they get expressed in terms of PDFs that integrate to one. So you need to learn probability in order to just like dogmatically wield it the way Bayesians do. But for 200 years, Bayesians were pretty much stumped by the denominator of Bayes' rule. Because if the parameters are continuous, in this case, we're thinking about theta as being a vector of size k, unknown parameters. So the denominator of Bayes' rule to get the density of the data irrespective of theta under the model entails a multivariate integral over the theta space. We've mostly just been doing like one-dimensional integrals, and even then very few of them are elementary. There's just practically none if you have to integrate k times to undeal this thing. But in 1990, that hurdle was sidestepped. Researchers, again, like I said, published a paper in Journal of American Statistical Association that showed how you could use many random draws on a computer, and computers were just barely then getting good enough to where you might be able to do this for real, rather than pen and paper solutions. Because there's just not that many situations where the prior is conjugate with the likelihood. And like I said, almost all of those are the case where you have just like one parameter. Whereas most things in science models these days are going to have many parameters to deal with. And this gives us a way forward for being able to approach those the modern way. Now, the modern way entails what's known as a Markov process. So a sequence of random variables defined by the fact that the future is conditionally independent of the past given the present. So tomorrow is conditionally independent of yesterday given today. But yesterday, today, and tomorrow are not marginally independent. They're just or the future tomorrow is conditionally independent of the past, given today, conditioning on today. And so if we let xt be the random variable governed by a Markov process, and so all we have to condition on is the previous realization, not all the realizations all the way back to the beginning of time. Then the joint PDF of all those, of x1, x2, of xt given x0, is just going to be the product of these conditional PDFs. So we can at least imagine the joint distribution, joint PDF, over all capital T random variables. And then we can at least imagine marginalizing out the first T minus 1 of those. So marginalize this over x1, marginalize this over x2, marginalize this over everything except the last one. So there's some distribution, if we do this like marginalization of a Markov process from the first time period up to the T minus 1, get rid of those, to leave us with some PDF of the last random variable conditional on the starting value x0, but irrespective of x1, x2, x3, all the way up to xt minus 1. And if we can figure out what that is, it's not too much of a stretch to think that as capital T gets large, the conditional distribution of the last one given the 0 with 1 approaches the marginal distribution of the last one, irrespective of x0. And that's true. And if that is true, then we can draw from this distribution that has this PDF by, starting with the x0 and then drawing x1 given x0 and then using that realization of x1 to draw x2 given x1 and draw x3 given x2 all the way up to whatever capital T is, draw that from its distribution given x t minus 1 and marginalize, if we do that process over and over and over again to marginalize out the intermediates, we get a whole bunch of draws from this marginal distribution of the last element, the teeth element of our Markov process. But this sounds like no easier than like Bayesian to do this. But we can make it a little bit simpler and hopefully get a little bit more intuition about it by considering autoregressive model of order 1, which is like the simplest Markov process because it's linear. Now what we actually use is not linear versions, but we'll do the linear one here to try to get a little bit more intuition. So an autoregressive process of order 1 specifies that x at time t is equal to m times the quantity 1 minus p plus p times x at t minus 1 plus epsilon t. And epsilon t is going to be distributed normal. It's the error term basically. It has expectation 0 and standard deviation s. So this is a Markov process in the sense that the conditional probability only depends on yesterday, not all the way back to the beginning of time in terms of how you do the conditioning. And in an autoregressive process of order 1, you can show, I'm not going to show it here, but well, I show it in the code, I'm not going to show it with proof, that asymptotically the teeth realization of this AR1 process is distributed normal, marginally, with expectation m and standard deviation equal to s divided by the square root of 1 minus p squared. This obviously presumes that absolute value of p is less than 1 in order for this denominator to be a real number here. And we can show that is true with code by this. So let's set capital T to 1,000. We're going to do this 10,000 times. set M and S and P to be, whatever we want. This is kind of, I had to squeeze the code in a little bit, so this is a terse way of writing, what we have here. So I have an AR1 function that does like that. And then the tidyverse way of doing this, which is not the clearest, but it allows you to do it in a small number of lines, is to call map double and reduce to basically come out with the last value of this process, R times. And you need an initial value for XO. But the theory of this implies it doesn't matter what XO is, asymptotically at least. And so I just draw the initial value from a Poisson distribution with expectation 10, just to get it going. And then if we calculate the difference between the average and what the average is said to be, and the difference between the standard deviation and what the standard deviation is said to be, those are all very close, not exactly the same, because this is a finite number of realizations, but it's certainly consistent with what we said to be true there. So rather than getting too, oops, I lost mine. Yeah. 1 second. It takes a long time to simulate the AR1 process 10,000 times. Okay, now we're going. Blah, 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 blah. Okay, so like I was saying, better to just visualize this. So on the vertical, horizontal here we have time, and then we have on the vertical the realization of X over time of this AR1 process. This was just 10 realizations. And so as you can see, the x0 starts with this draw from the Poisson, and it tends to be way out of step with what the distribution ultimately is, which was normal with the expectation of -1 and that business. But as you can see, it pretty quickly gets to a distribution that's not close to the x0 value with all 10 of these. And it looks like they all pretty much go to the same distribution. And it looks like it's kind of centered at -1, which is what I claim the distribution of the last element of these sequences is. Marginalizing over x1, x2, all the way up to x999. All right, so kind of keep that picture in mind. Now, so that's doing this R times. But what if we only executed the AR1 process once, but we kept the last few iterations, or time points, instead of just the very last one? Let's say we kept the last 100, or something like that. Let's call that R. So asymptotically, those are all still normal. Like the next to last one is still normal with expectation M and standard deviation S over the square root of 1 minus b squared, just like the last one. But the next to last one and the last one aren't independent of each other. They're explicitly dependent based on the AR1 dependent structure. So if you keep the last several of one AR1 process, they do have the right distribution, but they're not independent of each other, which affects the way you estimate stuff on the basis of this. And also, specifically just in an AR1 process, the correlation between two realizations that are plus or minus n steps apart from each other is p raised to the power n. So this is another reason why the absolute value of p has to be less than 1 in order for that dependence to go to 0 as n gets large. But if like n is reasonably big and p is somewhat close to zero, the dependence between these two is going to rapidly become very close to zero, even though it's not exactly zero. It's p to the. Okay, but in general, not just for the AR1 Markov process, but for any Markov process, if it mixes fast enough, which it's hard to verify, so I don't want to get into that, enough for a central limit theorem to hold for Markov chain Monte Carlo, then we can define the effective sample size as R divided by 1 plus 2 of the infinite sum of the correlation between two draws that are in iterations apart. So in the special case of an AR1, that's going to be p to the n. But in general, not just for the AR1, like you can estimate these things. And then the effective sample size would be R divided by 1 plus 2 times the sum of all those correlations between. And then the Markov chain Monte Carlo standard error when estimating the mean from the dependent draws that you have is going to be sigma divided by the square root of the effective sample size. So if all these things were uncorrelated, which they're not, all the p's were 0, then it would just be R over 1, and you would have the regular central limit theorem business for independent realizations of like sigma divided by the square root of R in the central limit theorem. But here, because they're dependent, it's sigma divided by the square root of the effective sample size, not R, the nominal sample size, due to the fact that the R draws that we keep are dependent on each other rather than independent of each other. And the MCMC algorithms in the 1990s, when this thing got started, it's usually some combination of give sampling, Metropolis Hastings, slice sampling, maybe some other couple other things. They tended to have very high autocorrelations, even when n was like 10 steps apart or 100 steps apart. You would get these correlations very close to 1. So this infinite sum, although it eventually, the correlations got converged to 0, so this is a well-defined infinite sum, like this decays. But it decays really slowly. And so even for 10, 100 steps apart, you can get these correlations that were very high, close to 1, and thus the effective sample size would be much lower than the nominal sample size. And you would see papers from the 1990s where they were like, I did 1 million iterations and it took me a month. Because they needed R to be like 1 million in order for NF to be like 7. To get effectively 7 draws from 1 million highly, highly dependent draws. And so that was like asymptotically valid, but not great. And we're not really going to spend any time learning about these 1990 algorithms because although some people do still use them, nobody should be using them. Because the MCMC algorithm in STAN, which was started in 2011 here at Columbia, but also today we're seeing some variations on the STAN idea that might actually be a little bit better, but we're just going to learn the STAN one over the past 10 years or so. They tend to have first order autocorrelation be negative. And the subsequent correlations for like moderate n being close to 0. And thus if you apply this formula and like the first one is negative and the rest of them are pretty close to 0, the denominator might actually be less than 1. In which case the effective sample size could be greater than the nominal sample size, or like about the same. Either way, it's not like a whole lot less, which was the problem that the sort of first generation MCMC algorithms had. And you can see the difference, like this is with p being -0.5, before it was +0.5. And you can see it sort of gets where it's going almost immediately and stays there and just moves around rapidly, as compared to this with the positive autocorrelation, where it kind of winds around. It gets farther away from its mean and stays farther away from its mean for like a decent amount of time. It's all like jaggedy and stuff. This is evidence of slower mixing in terms of the Markov process. And this picture right here is consistent with the fast mixing that Stan tends to give you by having this first order autocorrelation be negative and the subsequent ones being pretty close to zero. Like I said, the Stan one is actually a nonlinear thing, but you can still estimate the autocorrelations, and the first one tends to be negative. And that's a really good thing in light of this formula to make the denominator be like close to 1 at least. So that's some intuition as to why these days you can and should be using Stan rather than a less good in a variety of ways algorithms that they were using in the previous generation. So like it's more complicated than AR1, but you get some of the same intuition by just considering an AR1 process. So to motivate what Stan is doing, first we're going to take the natural logarithm of Bayes' rule. And the natural, like take the natural logarithm of both sides. And so logarithms turn products into sums of logarithms, or the difference in the case of a ratio. So now we're subtracting the logarithm of the probability of the data irrespective of the parameters, which we still don't know is, right? But we have a vector of k parameters theta, and what we're going to do is introduce a vector of size k called phi, which is another vector of k parameters that serves kind of like a catalyst. They're not of interest, substantively, but they're each going to get a normal prior, the phis will, with expectation 0 and some standard deviation s. So phis have normal prior. You can have any prior you want on the thetas, including normal. But anyway. Okay, so now we have twice as many parameters, and we still don't know this. Okay, next step is to define energy as the sum of potential energy and kinetic energy. So these are obviously physics terminology, and the algorithm in Stan is motivated by the metaphor of physics. Now, this is QMSS class. You're presumed not to know any physics. I don't really know any physics. Knowing physics is not necessary to use Stan, but you need to know that Stan uses physics. Now, to make this a little bit more palatable, one, the physics of this, like Hamilton figured it out in the 1800s. Like not even using any computers. Okay, so like that's a doable thing. Probably doable by like a physics major, like in undergraduate. Not even like Caltech or MIT or whatever, just, regular physics undergraduate could do this. So it's not like an impossible thing. And you don't have to personally do it, the computer does it. But it's not like it's a very solved problem. Moreover, like physics in the real world, like how would you land an airplane? Like that's kind of a complicated problem because like the real world has all kinds of complications to it. Like the weather and like the wind may change direction and you don't know exactly how much the plane weighs and all sorts of this. So like landing a plane is a somewhat difficult physics problem because of all the like things that you have to take into account. Doing a physics simulation on the computer, you can just assume there is no like other stuff. So nothing's like changing that you don't want to change. There's no like external forces or a plane that crosses in front of the runway while you're trying to land or stuff like this. So physics is as far as like Stan world is you should think of it as like, how does the physics in Angry Birds work? Not like, how does the physics of an actual bird work to like fly? You know, you just like angle it and you pull it back like the running out, and then it goes. And so the Angry Birds people like figured out the physics of that, and it's like no more complicated when standard. But anyway, define potential and kinetic energy, and we're going to take the logarithm of base rule here. It actually gets multiplied by -1 because like your people understanding of gravity is like things get pulled in the down direction, not the up direction, but multiplied by -1 doesn't fundamentally change things. And then we have the logarithm of the normal priors on the fees, which becomes a sum over k of the logarithm of a mean zero normal PDF with standard deviation s. Okay? So we got this. People know the physics even if you don't, and it's not that complicated. We still don't know this. The parameters are unknown, but we know that we have normal priors on them. And then we have this statement for total energy, which is also known as a Hamiltonian. So the fees, which are considered momentum parameters in this analogy, so momentum is velocity times mass. They don't enter the log likelihood. So when you condition on data, their distribution doesn't change. So the posterior distribution of the fees is the same as the prior of the fees, which is normal. They have different standard deviations, but is normal. And so then if we choose starting values for the parameters we actually care about, so that's going to be like the r equals 0 values, you can usually draw this from the prior, or you could even make them deterministic, whatever. And so then with the subsequent iterations, so we're going to do r to like 1,000, not a million. Like default is 1,000. For each of the iterations in this Markov process, we're going to draw the realizations of phi from their posterior distribution, which, like I said, is the same as their prior distribution, which is just normal. So R norm, draw. However many momentum parameters there are, capital K of them. And then on the rth iteration, we're going to recalculate total energy using the thetas from the previous iteration and the new realizations of the fees that we just took from independent draws from normal distributions. So then we're going to calculate H according to this formula here. So this is potential energy here, and this is kinetic energy there in the physics vocabulary. So what we say we're going to calculate, but like how could we do that if there's stuff in it that we still don't know? Well, Hamiltonian dynamics is a nonlinear Markov process. So it only depends on the one previous, not all the way back to the beginning of time. And then the future is conditionally independent of the past, given present. So Hamiltonian dynamics is going to involve all the parameters, the fees, the thetas, and the phi, over the metaphor of time, such that potential energy and kinetic energy are changing. But the total energy is said to be conserved, which is like a physics word, for H at the rth iteration stays the same. So like potential energy, if it goes up, kinetic energy has to go down by the exact same amount in that time interval in order for H to remain the same. And if potential energy goes down, kinetic energy has to go up by the exact same amount in order to make H constant. So H is this like iso energy thing. So the total remains the same. And that is important. You can get a little bit of intuition about this because it allows us to drop constants from potential energy function, because, well, one, we don't know them. But the one thing we do know about constants is they don't change. And because Hamiltonian dynamics preserves H, whatever the constants we don't know, they're getting preserved as constants. So we can just drop those from the H, and it means now our H, it just really changes the units of H, that's all. But the fact that those things are constants gets preserved. It just allows us to start to ignore them. And you'll see a little bit more why in a second. And so the fact that like the physics implies conservation of H is important when we're dealing with unknown constants. Now, I mentioned that within the rth iteration, we're going to evolve this over time, which means solving an initial value problem that's governed by Hamilton's system of ordinary differential equations. And so like you can do some math to show that the total derivative of the parameters with respect to time in this framework is the partial derivative of the Hamiltonian with respect to the momentum values phi. That's a vector. And similarly, the total derivative of phi with respect to time is the negative of the partial derivative of h with respect to theta. This fact preserves the fact, or makes the Hamiltonian be conserved, as the phis and the theta and the potential energy and the kinetic energy is all changing over time in such a way that total energy remains the same. So the derivative of the Hamiltonian with respect to the phis would actually be pretty easy. It's just like differentiate that, so it's 2, and the 2's cancel, and it'd be phi over s squared. So that's, or that should be s squared, but it'd be easy, modulo typos. But you might think, well, differentiating with respect to theta would be like a nightmare. Because, you know, you could have a million data points or something, and so you'd have to take like a million or more partial derivatives. So it's tedious at best for humans, but it's actually super easy for computers. That was another technological development. Like, how could you teach a computer calculus? But it's not so bad, really. I mean, there's a finite number of rules that the computer has to learn to like differentiate a bunch of functions. And then like you teach the computer the chain rule. It's okay, do the chain rule over a million links of your chain. Like, computers are good at that. And if we differentiate this unknown thing in the denominator of Bayes' rule, the density of the data irrespective of the parameters, we do know the derivative with respect to theta of something that does not depend on theta is 0. So that's the other element as to why we don't actually have to worry about the denominator of Bayes' rule in order to make this work. It's a constant, and the derivative of a constant with respect to a variable is 0. So that we know is true. An example of when like both the posterior and the momentum are standard normal, you can actually solve this system of equations analytically, and you get these equations, cosine and sine, for how the theta and the phi move according to the Hamiltonian physics. And you've got some unknown constants in this, r and a, but they can be specified at time 0, which is what we're doing when we like jump the new momentums and whatever. So anyway, the solution to this system of ordinary differential equations gives us updating rules for the thetas and the phis over time. Well, we usually can't solve this analytically, but again, we can do it numerically. And So in addition to like, okay, it preserves the constants, and so we can ignore those. Hamiltonian dynamics is also reversible. So you can go backward in time. Like if you go forward in time for 10 periods or whatever, and then decide you want to go backward in time 10 periods, you get back to where you started. That's an important physics like fact. It's also relevant for the MCMC, and it also preserves volume. And so all of those together implies that if we follow this process over time, it's going to produce draws of the theta and the phi that are not independent, but the PDF and proportional is going to be always proportional to the e raised to the power negative h. And so we're always drawing from that joint distribution of theta and phi, where the theta part is defined by the numerator of Bayes' rule. You can ignore this constant. And then the phi part is defined by this normal prior on those. And with Stan, you don't even see the draws of phi. We're just going to ignore those. And you can apply any function you want to the draws of theta, like we've been doing with much simpler ways of obtaining draws of theta. So, oh, come on. Where's my... I spent like an hour on this. Man. Okay, that did not work. But anyway, so all that maybe sounded like kind of okay. But it did presume that time is continuous. Whereas when we actually go to do this as standard Bayesian stuff, time is discretized into integers. So it's kind of like the old clocks, or like the clock on 60 Minutes, the TV show. It's like where like all of a sudden the second hand moves by 1 unit instead of like continuously moving over time. But the so-called leapfrog method, which was talked about in the reading, is really good for solving initial value problems numerically. It introduces a small amount of error each step because it's discretizing a fundamentally continuous deal. So there's a small amount of error. But if it's taking sufficiently small steps, then the error at one step, like if it's like a little bit positive, if the steps are small enough, then the error on the step after that tends to be a little bit negative. And so if you combine them together and sum over them, the errors kind of pretty much cancel with each other. But if the step size you're taking is too big, then the errors all tend to be in the same direction, and thus they accumulate. So if you're like a little bit too big on your first step, you'll be a little bit more too big on your second step, and a little bit more too big on your third step, and a little bit more too big on the next step. And then the error gets all accumulated, and that can cause what's called a divergent transition, where instead of, basically the theta and the phi, they break out of the simulation and just go to like Pluto. And then you know something bad happened with your discretization. Because in continuous time with like theoretical physics or whatever, that's not possible. In other words, this means that conservation of the Hamiltonian and the volume and all that doesn't happen in practice with the discretization like it would if we could do this in continuous time reveal. So Stan has a tuning parameter which is like a global step size that is tuned during like the first half of the iterations. But there's also some local tuning in the sense that the prior on phi, which I said was normal, with expectation S, or expectation 0 and standard deviation S, So the prior and the posterior are the same for that. But it's also going to tune the S, which affects the momentum for the real expected momentum for the variance of the momentum in the fees in order to try to get a good effective sample size, but not having divergent transitions. So to make the step size be sufficiently small so that the error is like mostly canceling, pretty negligible, but big enough momentum to where it can move around the parameter space fast and have tendency to have first order autocorrelation be negative, so that you get the instead of the. Alright? So that's that. Okay, part 5 of the explanation, which really does not do justice to what Stan is really doing. So you could simulate Hamiltonian dynamics forever. In like physics language, there's no friction. So if like the phi comes along and kicks the theta like that direction, and there's no like friction like there would be in the real world that has carpet, then it would just keep moving forever. Now, like it would go out the window, but imagine there was like a mountain over here. And so there's no friction, but there is a mountain. And I kick it that way. Well, it would go like part way up the mountain, stop instantaneously, and then roll back down the mountain toward me. And then, go past over there. But it would, if there's no friction, it just always stays moving. So, like, when do you stop? Which is to say, like, what's the ending condition of the initial value problem? So with Stan, like the time that it goes is also a random variable, because what Stan actually is doing is it uses the phi to kick the theta in like positive time direction and also negative time direction, just by multiplying by -1. And so Stan stops the process when the trajectories that start off going in opposite directions turn around and start to get closer to each other again. That's what's called the U-turn. And the no U-turn sampler in Stan says, okay, we're going to keep running this thing until positive time and negative time results in the theta getting closer to each other again. So they start off going in opposite directions and then they both turn around. And when they start to get closer to each other, we're like, we don't need to continue to do this anymore because they're just going to come back pretty much to where they started. And we already have like that information. So once the process stops, Stan is going to choose a realization of the parameters at discrete time step t with probability proportional to the posterior density. Again, because of the proportional stuff, you can ignore the denominator, really just work with the kernel. And so it's going to select a proposal for iteration R, and then it either accepts that proposal or rejects it by applying the metropolis criterion that was talked about in the meeting, albeit in a simpler context. So it's, if we could do this in continuous time, no error, we wouldn't need the metropolis criterion. We would accept every single realization because it would be just perfect. But because there's like a little bit of error, we need to do this. And what it really is like by default looking for is like accept 4 out of 5. Maybe reject 1 out of 5. And if you reject 1, then you just keep the previous realization and maintain that state another time forward, but then redraw the fees from the normal and start the process all over. And so that is a bit of an explanation for how the algorithm in Stan works to draw from phi and theta, but we're interested in theta. And the bottom line, the user only has to specify the numerator of Bayes' rule in logarithm form. And Stan can mostly handle the rest of it. And if it can't, it'll give you some warnings about what you can do. So this at least will work. So this person, Andrew Ghazi, made a YouTube video for the original Stan algorithm. It's a little bit different now, but same basic idea. For like a regression. So there's an intercept alpha, a slope beta, and a standard deviation of the error sigma. So this is a three-dimensional parameter space that the Hamilton physics discretized is happening in. So let's just run that. So you can see the different colors here correspond to the number of discrete steps. And you can see it starts out, it goes in two different like directions, even though it's like a three-dimensional spinning thing that eventually is going to make you nauseated. But they go, and then eventually it decides to stop. And then one of the places that it's been becomes the big green thing, which is the realization for iteration R. And then it keeps restarting it, and then it goes and it stops. And you get more and more floating green realizations from this three-dimensional parameter space. And because Stan, in a manner of speaking, is a greedy algorithm, it tries to keep this process going for as long as it can, each iteration. So keep it going for as long as it can in time to make both ends of this be as far apart as it can before they start to turn around and come back on each other. That is what tends to make the first order autocorrelation be negative. So where you are on iteration R tends to end up far away from where you were on iteration R minus 1. And that's good for the denominator of the effective sample size, because it tends to make it close to 1, and thus you get R divided by close to 1 effective draws from the parameters. And so you can see we're accumulating draws this way using a well-grounded physics process, which, like I said, if you're just doing it on a computer as a simulation as opposed to the real world, not much can go wrong. Now, Stan has its own computer language, in addition to like the algorithm and the mathematical library and the R package and like the Python, all that. But it includes its own computer language. Now, we're not going to learn the Stan computer language in this class, which is to say the Stan programs are going to be written for you or auto-generated by R syntax. So you only have to learn like R interface to Stan. It's not difficult to learn later, like if your data is in Python or something like that. It's actually an easier language to learn than R, because it's simpler. So here is like one, probably the only example that we'll have of this. This is like how you would do the problem 1.4 from the homework in Stan. So we have a data block that defines everything to the right of the vertical bar in base rule, like everything we're conditioning on. The A, the B, the V, the M, and then the observed data on the GDP for the fourth quarter. And then in the parameters block, we have everything to the left, your left, base rule. The unknown parameters, mu and tau. And then lastly, in this case, we have a model block, which is going to return target. So target gets initialized to 0, and then we add stuff to it so that by the end of the model block, target contains the numerator of base rule in logarithm form, ignoring any constants possibly that don't depend on mu or tau, which is what Stan needs to be its potential energy. It can combine with the kinetic energy to do the Hamiltonian stuff, to move around the parameter space randomly to get random draws of mu and tau. So we just say like, okay, the data are normal GDP with expectation mu and standard deviation is the reciprocal square root of tau. Stan parameterizes the normal distribution of the standard deviation. And then there's a gamma prior. So LPDF means log of PDF. Then there's the gamma prior on tau with shape A and rate B. And then we have a normal prior on mu with expectation M and standard deviation 1 over the square root of V times tau. Just like what it said in the. So all you have to do is tell Stan like those things. And it does not secretly know like this is conjugate. It's just like, okay, I've got a number target that is the value of potential energy with this mu and this tau, and it can do stuff. In a manner of speaking, it's not concluding anything. It just takes what you assert to be potential energy, and it does its physics. And you don't even have to mess with the derivative, because the C++ compiler knows like the chain rule, and it doesn't make mistakes like you if you try to do this with a big data set or whatever. Okay, so there are some warnings. We'll talk about this more like in the future next time. I just want to highlight the first point here, and McElwee does as well in the reading for today. The first generation MCMC algorithms, they didn't work great in the sense that the autocorrelation between two realizations that are n's iterations apart could still be pretty close to 1. It have very slow mixing. It could get stuck someplace for a long time, a long number of iterations. Such that your effective sample size could be like 2, even if you did like 100,000 nominal iterations. In which case, like best case scenario, okay, you're estimating mu, but you're effectively estimating it with 2 draws. Where like what we did with bowling or whatever, we were starting with 10 million and then we would keep like 100,000 or something like that. So we would have plenty of draws with which to estimate the parameter, and if we could calculate it analytically, like it always came out the same to like 2 or 3 decimal places. But if your effective sample size is awful, then you might not even be getting like 1 decimal place correct. And that was because, in part, there was so much positive dependence in the draws, and the original algorithms didn't have good ways to tell if something was going wrong from the draws. Like the only way you could tell the draws were wrong is if you had the analytical posterior closed form with conjugacy or whatever to compare it to. If you didn't have the analytical thing, you just had the draws, you had no real way of knowing like, is this like pretty good or pretty bad. But with Stan, because of like the physics underlying it, and it's like this should stay the same, and this should stay the same. And then, okay, the computer, the screen data, there's a little bit of error, but if there's like a lot of error, we're gonna know. And we will give you a warning that you should really heed, saying, this is not going so well, the step size was too big, like, here's some stuff you can do about it. We'll talk about this more later. But McElwee like harps on this, and it's really true, and it gets back to one of the things we were saying the first week, like uncertainty as to whether software works as intended, which is like hard to quantify probabilistically, but it's pretty easy and very reliable with almost no false positives for Stan to give you warnings when like the physics gets violated. And so that's kind of, the physics is like the reference point. Like this should stay constant total energy, and if it's changing, then like we know something bad happened. And we can make a warning to that effect, and we can make some plots about it. we'll see how to do those sorts of things. But anyway, that is a very good thing scientifically, because when you don't get the warnings, you're pretty well assured that it drew from the posterior distribution you said. And then it's just a question, is that a useful posterior distribution substantively? Okay, out of time for today. I'm going to stop the stream. No new homework.